Hey guys, what's up? Sorry for this kind of change of format. I'm just not feeling well. My fiance is not either. There's something going around his office, and I just didn't want to bring it in to you guys. So I figured we're better off doing it this way. If you have any questions, let me know. I am just gonna assume if I ask for questions and I get silence, I'm gonna assume that there are no questions because I know most of you kind of just stay on mute. That being said, if you have a question, just interject it because I may forget to ask. Since I don't see the faces today. And then pardon the sniffles too. Okay, so our homework is due next week. I'm also recording this just so you all know. So I'll post it on Canvas. Um, our homework is due next Tuesday. So this is the first set of questions and it'll be online. It is online already. It's on Canvas in your assignment section. Last week we did kind of the fundamentals. I would say if I were to rewrite this table, I would put that last week we focused on force triangles, finding the resultant force from the triangle, and all that. This week we're going to do, it says force vectors, unit vectors. We'll talk about those. Equilibrium on a particle, we've already started talking about. I would say the focus of this week is the XY component method, and we'll go into some details of what that is. Thing I'm frozen. There we go. Okay. Yeah. Okay. So we had a couple of things. We were mostly threes and fours, with maybe 1 5 in there. Um, Law of sines and cosines. Being asked, what's being asked for in rewriting the formulas? I think that's having to do with the problem solving methods. Free body diagrams, how do you know what free body diagram to draw? If you have any homeworks on if you have any questions on homework, you can email me. I tend to end up in Canvas more often than email. So if you send me a Canvas message, that's probably um, better. It's probably the best option. Um, just in that I'll get back to you faster. Um, but yes, absolutely, you can email me. Um, okay. A little more review on the trig functions, and angle rules. Trig, took it in high school. I think that's the case for a couple people. Skewed resultant. I think this is more time. Um, okay, perfect. Let's see. I think I have a few review slides in the beginning. So we didn't really have much on setting these up, much in terms of questions on it. So just know that these are in your Canvas slides. If you do want to see a little more review on triangle or trapezoid. I think that was also in our last week's slides as well. Okay, when we look at this, um, I mentioned in class that when we look at the R equals P plus Q, the second line here, those should all have that vector symbol on top of it. Just kind of that line. Um, and that saying that is taking into account both magnitude and direction. Our law of cosines, the way that we write it standard, most often, and the way that we would see it on probably a test, and most often on our homework, is going to be r squared, meaning our resultant squared equals p squared plus q squared minus 2pq cosine b. P and q are going to be our component forces, and then b is going to be the angle. B or beta, sometimes I'll go back and forth between the two. It's going to be the angle opposite the resultant. If we were looking for if we had all of our side magnitudes, and we had, say, angle A instead of angle B, then we could set up our equation as q squared equals r squared plus p squared minus 2rq cosine A. So you can move that around if you had this angle, but you were looking for a different side, you would have to rearrange your equation and so on. Good rule of thumb is for the sine rule, you're obviously going to have one on either opposite. You're going to have a set, an angle and its opposite side magnitude in order to have at least one full term, and then you'll have to have one thing from each of the other terms in order to do that. We wanted to see a little more of this. So here's kind of the different versions. So if you were to have, we would picture B as the resultant force. Usually our resultant force is going to be larger as long as our magnitudes are complementing each other. The other two vectors are complementing each other. So this middle one is the one that we're most used to seeing, but we could see it in other formats for other angles. Okay. The law of cosines. Let's see if we can get a problem with one of these things. See if at the end we have. Okay. I'm gonna just keep going in order of the slides. We can revisit law of sines and law of cosines to kind of go deeper. That may be a Friday thing. Okay. So we mentioned when we were talking about our Cartesian coordinate system, that's our standard X and Y. We mentioned that we've kind of talked about things going completely in the X direction, completely in the Y direction, or some combination of the both of them. So we were also talking week one about taking component vectors and adding them to create a resultant vector. So now kind of picture, we can do the opposite as well, right? We can go from one resultant vector or one vector that's a combination of two other vectors into its two parts. So an example that is going to come up frequently as in something that makes it easier to solve problems is to break a force into its X and Y components. Again, picture all these X boxes to be that vector symbol. Let's see if I can that symbol, right? So the force vector is equal to the force along the X direction vector plus the force along the Y direction vector. We can break that up further by assigning what we call unit vectors. Now, how do I get rid of that line? Unit vectors, you might remember them. You may have been exposed to them in math class potentially. Our I vector is going to be our X vector. So this first vector symbol that I did is just kind of your generic vector symbol. So you'll see it on like the forces that we saw earlier and all that. The other symbol you might see that is an I as well is like a little TP. And that's the symbol for a unit vector. Unit vector has a magnitude of 1, so really all it's telling us is a direction and not a magnitude. So our I is our X direction and our J, so that would be a J vector, this would be a J unit vector, is our Y direction. I don't know if I misspoke a second ago. Our I is our X direction, our J is our Y direction. You'll see me probably interchange the symbols on top, and sometimes even forget it, but that's the technical difference between those two. Okay. So a unit vector gives us a direction. It has a magnitude of 1. So if we were to multiply anything by the unit vector, if we were to have a magnitude of a force, meaning the strength of a force, and we were to multiply it by the unit vector, the unit vector would apply that direction to that magnitude. So say we had a 100-pound force in the x direction, we could say 100 pounds. 100 pounds would be the magnitude, and then I would be your unit vector. That would give you the directional information. Let's see. So this is the most common thing you'll kind of see. I caution people. So the XY component method is basically breaking forces up into their X and Y elements. And that way we can just sum the X elements, sum the Y elements, and see what their resultant force is that way, right? It's another method to find a resultant force. So how do we break a force into its X and Y directions? One element is using trig. I caution you to be careful with the equations on this sheet, because these are only going to apply if you're working in the first quadrant, right? First quadrant meaning positive X, positive Y. Okay, that's not true either. So if your angle is from the positive Y axis, then it will work. So let's say you had a 45-degree angle here, it's gonna work. Let's say you had a 90-degree plus 45-degree, what would that be? 135-degree angle. And you were to put 135 in this angle information, that would still give you a correct answer. The issue is when we start getting angles in different areas. So let's say we have a vector here and we were given this angle. A common mistake is to then just plug this into these equations. So the two ways that you can solve these are either by having the angle always being the angle from 0x, meaning you're always going to, let's say you were given this angle instead of this one. You would do like a 180 minus theta and then do the equation. Is this making sense? Any questions? Okay. The other option is to logic it out using your trig. Where's my thing? So let's say, still want me erasing. Okay. So let's say let's go back to this scenario where this is the angle, right? We could turn this into a triangle, a right triangle, and use our SOHCAHTOA or this one. That thing. We can use that to solve for the X and Y elements, right? So just be cautious. Be cautious with what angles you're using, and how they would apply. Let's get rid of this on the bottom too. Make sure everybody is in as well. Okay. Okay. So here would be kind of our format of saying that our force vector is equal to the magnitude of the force in the x direction along that x vector, along our I vector, which is the x direction, plus f of y. F sub y is going to be the magnitude of the force along the y direction, times j is that vector, the y vector. So, ooh, yeah, I'm so sorry about that. Yeah, I know it's not ideal. It brings up another point though that I know some, and I'm assuming anybody getting in now is about a similar case. Um, what was I saying? I know some classes will have a Discord where they'll discuss like if there's questions on homework, if there's questions on anything like that, and also to kind of communicate about stuff like this. If you guys want to set something like that up or a text message group, just so that if anything like this happens again, one of you can just send it to all of you and hopefully we can avoid it. I really do apologize. I just didn't, especially with the state of the world right now, I didn't want to chance it coming in sick and all that. So adding forces using the X and Y method then opens us up to be able to have more forces, right? So here is an example. This is a 3-force example, but we have this vector P, this vector Q, and this vector S. Somebody said one of the questions from last week was how to know what you should draw a free body diagram about or of. For our particle physics or our week 1 and 2 sections, it's gonna be just basically a dot with arrows in the directions that the forces are going. As we get into, so the next unit is going to be our rigid bodies or our 2D. Then it's going to start mattering more, but we'll talk about kind of how to create the boundaries of our free body diagram. But essentially, the resultant force is the x component of the resulting force is the sum of all of the other x components, the x components of all the component forces, and the y resultant force is the sum of the y component forces. So if we break each force up into its x and y, we can easily find the resultant force. The magnitude of the resultant force is going to be, that's going to be our Pythagorean theorem that we use to find that. So our a squared plus b squared equals c squared. Our a and b are our resultant force y component and our resultant force x component, and our resultant force magnitude is the c in that case. We're also going to need to find the angle of the resultant force, and that you're going to have to use your trig for. And then, of course, be careful, particularly with this one, because this one will not give you, just based on how trig works, this is going to give you a value in the first, said first trimester, first quadrant. My goodness, you guys. Okay. Okay. So let's do a quick time shift, 10:20. So here is our first sample problem. We have force 1, F1 is 150 newtons, F2 is 80 newtons, F3 is 110, and F4 is 100. So our free body diagram for this one is going to be our point A. I don't know where to do this. We'll go down here. Our point A, with the forces going out of it. So we're going to have a force of 150, a force of 100, a force of 110, and a force of 80. And then you're also going to have your angles on the free body diagram. I'm not going to draw them in just because if we were to just turn this into a point, that's essentially our free body diagram in this case. But we'll just leave it at that. Okay. Okay, so that's our free body diagram. Our haves and our needs in this case, what we have is all of our component force magnitudes and directions, and we need to find the resultant force. Oops. So using the XY component method, we're going to break all of these forces up into their X and Y parts. I like to, where is it? I go real into detail on this one just so you guys can follow it when I'm not around. But I like tables for this particularly, just to keep everything straight. And then the resultant force, so right here, this table is the force. What force vector are we looking at? F12, kind of the name of it. The magnitude, what's the amount, the strength. The X component and the Y component, you would then use your magnitude and the geometry of where it's going to find those components. So let's go to our first force, F1. So F1 is 30 degrees above the x-axis. The magnitude is 150. And what did we want to find? The x and y directions. So we can use our trig. In this case, because it is our first quadrant, we can just use those equations to find the answer, find the solution. So for any questions on that? Okay. For force 2, which is in the second quadrant, we would not be able to just use our trig if we were to use 20 degrees. We could use these equations if we were to do 90 plus 20. So that would be 110 degrees. So some students do that. That's usually what I would do as well, is just to do the angle from the positive x-axis. But the alternative option to that would be to create a triangle. This is 80 degrees. This is 80 newtons, 20 degrees, and that will give us enough information to find our x and y elements. Questions on that? F2. Okay. 3 is probably the easiest one or the most intuitive. It is going completely along the negative y-axis. There's no x element. So the magnitude of the x element of F3 is 0, and the y element is the full magnitude of the force, which is 110 newtons. So this would represent this would be vector notation of force 3. If you ever hear me say the term vector notation, that's kind of what we're talking about, where it's our x and our y. And then if we're talking 3 dimensions, you're going to have a third there. We're not quite there yet. So what I would do for F4 is I would do a negative 15 degrees, and then your trig would work out just fine. Yeah. The other option would be 360 minus the 15, or you can do the triangle with 15 and kind of logic out what goes where. Questions up to here? This is also all being recorded just for anybody who, I know I saw some people come in a little late, and again, I apologize for that. Okay, so once we have our table filled out with our forces and their x components and their y components, we can sum our x components, sum our y components, and that gives us our resultant force x and y components, which gives us the opportunity to create another right triangle, where we can calculate the magnitude of the resultant force. We can calculate the magnitude of the resultant force, and we can calculate the angle of the resultant force. Again, be careful with the angle. What angle is this tangent giving you? Because if we're not in the first quadrant, you might have to add something to that. Okay, any questions? Cool. We started talking about equilibrium a little bit last week. Equilibrium means that all of your forces are balanced, that you're not being pushed in any direction more so than any other direction. So your x components are going to sum to 0 and your y components are going to sum to 0. Okay. Here is kind of a clearer picture on a free body diagram. So a space diagram is a picture that we're going to get is a diagram. It's a diagram that takes into consideration the size and shape and space of the objects and what everything is. The free body diagram simples it down to being just what is really important. So in this case, what we're analyzing is point A. There's a weight pulling down from that. And then there's two tensions from cables pulling upward on an angle. And that simplifies to this. So let's say the boundaries of our free body diagram are right around here. Okay, so you kind of create the boundaries of your diagram, and any line you're breaking, you want to introduce a force there. Very cool. Any questions? I am going to skip ahead of some of this and just kind of see what else we have. Let's look at this one, because this one I have pretty clear. Okay. So we have a ship unloading a car. It's unloading a 3,500-pound automobile supported by a cable. The rope is tied to a cable and pulled to the center the automobile over its intended position. What is the tension in the rope? I don't feel like they really said it very clearly in this one. I'm assuming, and it is because this class is statics, that rope pulled the car to the center, and we're now holding that car in the center. So our car is not moving. So our car is in equilibrium. Usually it's a little more clear in the wording, but this situation is in equilibrium, meaning all of our forces are going to be balanced. Okay, let's start with what do we have? What do we need? So in our problem statement, or our words of our question, we have the weight of the weight of the downward force, the weight of the car. We need the tension in rope AC, ABC, and then we have the direction of both of those forces. So we have magnitude and direction of one force and direction of two forces. Our free body diagram would have point A. That tension of AC is going where that person is pulling that car at 30 degrees below the x-axis. Weight of the car is completely in the y direction, or the negative j direction. And then we have this force over here, and this is that zigzag alternate interior angles that we've been kind of seeing a little bit of. Okay. Questions? Cool. So now, if we were to take our points, there's two ways to use the triangle rule. Triangle rule that we talked about last week. So the first way to use the triangle rule is to find a resultant, which is what we did last week, where I wonder if I have a good one here. Yeah. To find a resultant force where our two component forces were going in one direction, and we want to find the resultant force. When you have something in equilibrium, it's going to create a closed polygon. So if you're trying to find a resultant, the resultant would be what's keeping you from being in equilibrium. So that is going to be what closes the polygon. So that was our first method. So in our first method, you're trying to find a resultant. You're going to see two component directions going in like the same direction, kind of. Going head to tail, we'll say that. Two component forces going head to tail, and then the resultant force goes from the tail of the first to the head of both of them. So that's our first method. I'm going to say all of this again on Friday, just so that I can kind of say it more animated and use the board and stuff. But the second way to use the triangle rule is if you have something in equilibrium, you know it's going to create a closed triangle. Where was that question? Here it is. So when we have a situation that we're using the triangle rule in equilibrium, we're going to have all of our forces go head to tail in complementary directions. So it's either going to go counterclockwise, all counterclockwise, or all clockwise. In this case, I like to start with anything that's in one direction, not the band. Anything that's completely in one Cartesian coordinate vector direction. So start with that 3,500, then tack on whatever is easiest. If you were to have put this one next, then your AC would still bring you back to create that other half of that triangle. But that'll create our triangle for us there. Let's see if we can get the geometry here. So since this A is, I know there was a question for another skewed vector. I'm not going to do that today, but I will find a question for that. For like if this 3,500 was a little bit skewed, but it's not. So the angle between TAB and that 3,500 is going to be the same as the angle between TAB and that y-axis. So that's where we get that 2 degrees from. Let's see, TAC is 30 degrees below the x-axis, so this would be 30. And then what? And then this would be 90, and that would get us our 120. And then let's erase that. And then we would have the 180 minus 120 minus 2. That's going to get us our 58, our last measurement here. Okay, so now we have one set of opposing angle and magnitude, right? That 58 and that 3,500. And then we have the two other angles, so we can use our law of sines there. And do the sine of 58 over 3,500 is equal to the other two proportions. Okay. And here is that worked out. Any questions on that? Okay. I think let's do this one in class on Friday. Any questions? Is there anything else you guys need from me today?
Is the homework that's due on next week, is it from the book or is it already on Canvas?
It is on Canvas. I think you should be able to find it on the book as well.
Like the only reason I'm asking is because hold on, let me turn my camera on for a second. The only reason I'm asking is because I'm currently a little bit. I've been doing a lot of spending for other classes, and it's going to take me a bit before I actually get the book itself. So
No, yeah, no, it's all available online. I don't even remember what year it is though right now. Clicking the wrong classes. 23. 2. There we go. I haven't got all of them up yet. But you guys should see at least 1, 2, and 3. And if you click in, there's a zip file that has the questions in it. So you don't need to have the textbook for this class. It is an open book class or open book tests. That being said, I don't know how much the textbook helps, because most stuff should be in the slides, in notes. I also know you have free printing. So usually somebody in the class is able to find a PDF version of the textbook, and then you can print out any pages that you think might help or anything like that. Some people do still buy the textbook just because that's how they learn better, but it's not required.
I mean, well, I've tried to find a PDF online. Like I've tried a lot of different sites, and they always usually lead to a different site or potentially a virus. So I tried myself.
Natalie was able to find the PDF. So
I mean, if you could send it, that would be a godsend, because I tried. I almost destroyed my devices. I can't have that happen.
Yeah, I don't think I can facilitate the exchange of it. But yeah, her email is right here.
Thank you.
Yeah. Okay. Anything else? Okay, cool.
Just to clarify, for the homework, are we handing in like physical pages with our work on it?
No, virtual copy is fine. Some people do it in like they do it virtually. Some people write it out and take a picture or scan it. Either is fine.
Okay, thank you.
All right. Anything else? Yep, submitting homework on Canvas. And it's due right before class on Tuesday. Okay, cool guys. I will see you all on Friday.
Have a good one. Feel better.
Thank you so much. Have a good one.